Good morning, everyone. Welcome back. So, last time we talked about the basics of power systems, and so what we discussed. So we talked about phasor notation and AC power system and impedance, power factor, and power lagging. So I think we stopped somewhere around here. So let me start from this page. So this was the example. We have a voltage source, we have a line impedance 5 plus J 40 ohm, and the load impedance or resistance is just 100 ohm. And here the aim was to maintain the voltage at the load side to 40 kilovolt. And so assuming, this is a voltage source, this is a load side, and each load requires some voltage. So here our assumption is that this load requires 40 kilovolt. So assuming this voltage at the load side, we computed the current. This is easy, it's V over Z. So voltage over impedance, and then we can compute the current. And this is a simple circuit. And we compute the current, and we know the total impedance or the voltage drop here and the current, so we can compute the voltage drop across the line impedance. So that's this part. So we computed the source voltage that is represented like that using phasor notation. So the magnitude is 44.9 kilovolt, and this is the angle. Okay, and then the complex power, complex voltage times the conjugate of complex current, VI conjugate. And then when you compute, the complex power at the source node is this much. This is the magnitude, and this is the angle. Or active power and reactive power, okay? So in this example, we only have a pure resistive load. And in next example, we change the load condition such that this load is inductive load. So most motor-based load is an inductive load. So that's why we have a coil here. So the impedance of the load is 100 plus J 100 ohm. So this is the impedance of the load. So phasor notation like that. And this load is 0.7 lagging. Actually, this is a 100 ohm, and this is J 100 ohm. So this is a square root 2, 100. So this is a theta angle. And the cosine theta is 1 over square root 2. So, over 2. So this is 0.707. So, the power factor is roughly 0.7. And here, focus on this part. We want to maintain the load voltage same as before, like 40 kilovolt, and here 40 kilovolt, and we only change the load impedance. Actually, the load impedance has changed to that value. And then the current changes, and the voltage source changes, and we want to compute that. So using, and here anyway, our assumption is that we want to maintain the load voltage as 40 kilovolt. So using this impedance at the load and using this voltage, you can compute what? You can compute this load. Can you do that? Yeah, obviously. So from here, you can compute the current at the load side. And after you compute the current, then you can compute, this is that. And then you can compute the voltage drop across here, I times Z. And then this 40 kilovolt plus the voltage drop here, it gives you this value. Okay, just a simple calculation. And then the complex power at the source side is V times I conjugate, and you get this number. So Yeah, computation is easy, but I hope you to compare this example and the previous example. You know, the complex power at the voltage source, magnitude and angle. Here the magnitude and the angle. Or you can check the active power and reactive power. Here the active power and reactive power. And also one more thing, the current. The current magnitude is just 400, and here the current magnitude is 564. So what does this imply? Example 1 and example 2. Which is a better case? Better in terms of what? Minjae, how are you today? Yeah, so example 1, example 2, which one do you prefer? And what is the reason? In terms of what do you prefer? Which example? Hojin. And what is the reason?
로드에 걸리는 부하가 비슷한데 파워를 더 많이 필요합니다.
Yeah, so here the current magnitude is 400. Here the current magnitude is higher than that. That means higher current incurs more power losses in the transmission line. Okay, and also when you look at the complex power at the source side, the active power and reactive power, the required active power is increased. The reason is because we have more power losses in the transmission line. Okay, and the reason is because of that inductive component, the power factor changes, and then the ideal case, in the ideal case, the power factor should be close to 1, like 0.95, almost close to 1. It is not easy to make it perfectly 1 because anyway, the load has some inductive component. Okay, so yeah, example 2 needs higher source voltage to maintain load voltage as 40 kilovolt when reactive power load is added to circuit and the current becomes higher than before. Okay, so now you see the role of inductive load in a negative way and the meaning of power factor. Okay, so what we want to do next is to correct this power factor, and one of the mechanisms is to add capacitive load. Okay, I will discuss that later. And let's think about the power system notation. And this is called single line diagram. And this is equivalent to this circuit diagram. So in power system, using this kind of single line diagram is much more popular than this kind of circuit diagram. The reason is because this is simpler. Okay, so here when you look at this, we have a voltage source or generator side, and we have a load side, and we have a transmission line like that. Okay, and in the circuit diagram, you are used to this kind of circuit diagram. This is a closed loop, right? So we have one wire and another wire, and we have loads here. But in a single line diagram, we do not have return path. Okay. So, okay. Active power, reactive power. And that is denoted here, active power and reactive power. And this symbol is used to represent bus. Bus or node. Okay, so physically, this bus is a huge metal plate, like a copper plate. That metal plate is like this huge. Okay, so we have a generator, and the generator is connected to this metal plate, and this metal plate is connected to a transmission line. Okay, that means anything that is connected to a common bus is assumed to be connected with zero resistance, ideally. Okay. And at the load side, here we want to keep this load voltage as 40 kilovolt. Okay, so the voltage here, and the active power consumption and reactive power consumption. By the way, how can you compute these two? Well, you know the voltage at the load side and the current at the load side. Okay, so S equals V times I conjugate. You can compute that, and this is the result. And this is typo, this should be plus, okay? Okay, so generators are shown as circles. Arrows are used to show loads. And transmission lines are shown as a single line, okay? So when we describe power systems, so this is the most simplest single line diagram. One voltage source and one load and one transmission line. But later, no, this is a node or bus, another node or bus, and then we will have a graph. And that graph is something like this. So we have a node, another node, so this is connected like that, this is that, but maybe we have another node. So I think you already saw this kind of line diagram before. So we have this kind of connection, and this kind of connection, and this kind of connection. So 3 bus systems. For example, one generator, another generator, and just a load. Okay, and you can add more and more node, and then they can be connected like this, depending on the situation. Okay, so we have a graph. A graph is a collection of node and the lines. Okay, but it has corresponding physical circuit diagram as well. You should be able to imagine that, but don't need to do that all the time because this is simpler. Okay, what we want to do here is that we want to put a capacitive load here to improve power factor. Okay, so let's see how we can do that. Yeah, reactive, that is called reactive compensation. Okay, here, we compute this current and we know the impedance, so actually we know the voltage, so V times I conjugate gives you this one. So we have active power and reactive power, and we want to remove this part, and one way to do that is to put capacitance at the load side, and physically that is achieved by put capacitor here in parallel. Okay, in parallel. Of course, you may want to put the capacitor in series to improve the power factor. That is possible, but the problem is yeah, this is load side. We have a resistance component and inductive component. This is our load. And then, of course, it is not impossible to put some capacitor here to improve power factor. But what's the problem of doing this kind of job? This capacitor need to put here. That means you need to cut line and put capacitor and rewiring again, and that is not recommended. Okay, So putting component in parallel is much more easy, much easier. Okay, because no, you can just put, how can I say, yeah, capacitor and then connect this 2 point. That's it. Let's put the capacitor in parallel, right? So putting capacitor in this way. And physically, okay, you know, when this is R and J omega L, and the impedance, this is J omega 1 over J omega C. This is the impedance of coil and capacitor. And then when you focus on this part, what is the impedance of these two components connected in parallel? That is what? Z1, Z2, we have two components and they are connected in parallel. Then what is the composite impedance? What is that? You know that. This comes from 1 over Z is 1 over Z1 plus 1 over Z2. You remember this, right? The current, no, voltage is same, so the current go through here is the sum of this current and sum of that current, right? So when voltage V is applied here, V, the current is the sum of the current for this branch and another branch, right? So from here, you get that. Okay. Anyway, just memorize it. So, in this case, the impedance is J omega L times J omega C and J omega L plus. So cancel, cancel. Anyway, this is some constant, and we need to focus on this part. And what happens if you choose carefully this value of C? So when we do power factor correction, what do you want to do? We want to make this part is like does not exist at all, right? So we want to make it purely resistive load. And how can you do that? Make the impedance, this part, infinite. How can you do that? Make this part 0. Right? So that's why you have if you choose the capacitance that satisfy this equation, then you can make this impedance infinite. Okay? And we only have a pure resistive load, and the power factor is 1. Right? So, yeah. So omega square LC should be 1. So no, this is 2 pi times F. So when we know L here, you can determine C to make the load as a purely resistive load. Okay. But if you think this is complicated, then just you can say we put a reactive, okay, we inject reactive power here. So this is the reactive power consumption at the coil, and then we put capacitance that inject reactive power or generated in the reactive power minus 16 megabar. Okay, so yeah, that is this one. Just put capacitor that can supply 16 megavar reactive power. Or, yeah, this is easy, but then how can you choose C? You can choose C that satisfy this one, but from this kind of explanation, how can you choose C? Do you see what I'm saying? Anyway, we want to put passive capacitor there, right? And then you can choose the capacitance. But no. Okay, we have this reactive power component. So I want to compensate that. Reactive power consumption and reactive power supply. Yeah. And you need to choose C. How can you do that without using this one? Yeah. Actually, we discussed that here. Power consumption in device. P equals I square R. You know that. And for inductive load, similarly, I square times omega L. And for capacitor, I square times XC, and this XC is 1 over omega C. Okay. Or V square over XC. So this is 16 megabar. And this minus means supply the reactive power. Okay, so we know the voltage, so you can compute XC, and you can determine the capacitance. Any questions? Easy. Yeah. Anyway, I will give you some homework problems, so then you can get used to this stuff. Okay, key idea of reactive power compensation is to supply reactive power locally, not from here, locally, and that is easily done by just putting passive capacitor at the load side. Okay, so in the previous example, this can be done by adding 16 megabar capacitor at the load. Compensated circuit is identical. Oh, so this compensated circuit, so by putting this, actually, no, you can assume that this part and this part never exist. So this is identical to, compensated circuit is identical to first example with just real power load. Is it? So actually this is the result. Active power and reactive power. Active power and reactive power. Are they same? Yeah, they are same, right? And the physical meaning of that is, make the impedance of this part infinite. Okay. Any question? No question? Okay. Reactive power compensation continued. Reactive compensation decreased the line flow from 464 amperes to 400 amperes. No, as we said before, 400 and this much. Okay, so by doing reactive power compensation, we decrease the line current. And what is the advantage of power compensation, power factor compensation? The line current decreases. That means less power losses in the transmission line, the I square R term. Okay, line losses which are equal to I square R decrease. And lower current allows use of small wires. Okay, well, what does that mean? Actually, I don't want to go into detail into that part, but the typical power system textbook has one chapter for specifically for the transmission line. So the transmission line, this is a copper, okay? This is a metal. It has a center, and then current flows like that. And actually, this is a complicated story, but we have surface current, blah, 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 some side effect. So I don't want to talk about that. Anyway, to let the flow go through this wire, we need to have some area, to let a large current flow, this intersection should have a large area. Okay, that means it requires more material, copper, that is cost actually. So we want to use less copper material to install the transmission line. Okay, so lower current allows use of smaller wires, or alternatively supply more load over the same wires. And voltage drop on the line is less. So this kind of, that example was very simple, but the reactive compensation is used extensively throughout transmission and distribution systems. And so when you, I will show you the figure shortly. And the capacitors can be used to correct a loss power factor to an arbitrary value. Okay? To choose C properly, we can make power factor 1, but 0.95 is typically good enough. Okay? Anyway, by putting some capacitors, we can make power factor an arbitrary value. Power factor correction example. Okay, assume we have 100 kilo VA load with power factor 0.8 lagging. 0.8 lagging is what? This is zeta. Cosine zeta is 4/5. So this is 5/3. Then this angle is what? 36.9 degree. Assume that, and we would like to correct the power factor to 0.95 lagging. That means, we want to make like that. So cosine zeta should be 0.95. Then what you need to do is you want to put capacitor here, and you want to change the impedance where the cosine zeta has this value, right? So, or simply, okay, we have complex power, 100 kilo VA. So this is 80, and this is 60, and this is 100. And power factor 0.95 requires this zeta is 8.2 degree. So this is 8.2 degree. And then so this is a reactive power, and you put reactive power in injection. So 60 minus Q cap is this much, right? And we know that this angle is 18.2 degree. So tangent 8.2 degree is this over that. So 60 minus Q cap over 80 is this one. And then Q cap is computed like that. So that means we need to inject reactive power this much at the load side. How can we do that? Choosing some capacitor that can provide this much reactive power, right? Yeah. Any questions? Some questions? No questions. So far, so good. Yeah, so this is a distribution system capacitors. You can see this on 서강대 길 or 백범로. When you walk through the street, you can see this pole and the distribution line, and also you can see this kind of capacitors. These capacitors are for power factor compensation. They are just capacitors. They are just passive component, okay? And they are called, so you see several capacitors, 1, 2, 3, 4, blah, blah, blah. So they are called capacitor bank, okay? And that kind of capacitor bank is a passive component, just a capacitor, okay? Just a larger one. And so they are passive. just capacitor. But you can use semiconductor to make to the power factor correction. And one of the example is using SVC. This is static VAR compensator. And in this case, you need to use semiconductor and the capacitor, a combination of that. Anyway, this is also a passive component. Okay. So let's check SVC. Yeah. What is static VAR compensator? The static VAR compensator looks like that. No. Capacitance, no, some diode. No, okay. And also, no, another types of component is the StatCom. StatCom is based on power electronics. That is also used for power factor correction. So StatCom. 스택컴은 전력 배전 과정에서 손실되는 전력을 연속적으로 조절해 전력 계통의 전압을 일정하게 유지하는 설비입니다. Blah blah blah. Okay. So reactive power, so I only explained reactive power in terms of power factor correction, but this reactive power is also related with voltage magnitude. Okay, and because we want to keep the voltage in some range, especially in the distribution network, we need to inject reactive power sometimes. Okay, and then StatCom can do that. So just be familiar with that kind of terminology.
저런 플래닝은 우리나라에서 캡코가
where to put this kind of yeah. Capco maintains the transmission line, distribution line, and then yeah. So because a lot of renewable generations are integrated into the distribution network, the voltage fluctuates severely these days. So we need to have more of these devices. And ESS can do that anyway, because ESS can inject active power or reactive power. How can we do that? Just change, control the angle between voltage and current. Okay? This is power factor 1, this is power factor 0. So the ESS, the PCS, power conditioning system can do that. Change the angle between the voltage and current. Okay? So ESS can observe or inject reactive power. Okay? Or the photovoltaic generator has an inverter. Okay, I didn't explain inverter yet, but inverter means it changes the DC voltage to AC voltage. When the inverter does that, it also can change the angle between voltage and current, which means it can inject reactive power or observe reactive power. Okay, so those things are the control mechanisms in distribution networks. Okay. Next topic is three-phase system. What is three-phase system? I think you already learned this, except Hyung-suk. All of you learned this in circuit theory. Okay, so you remember what it is. You don't remember what it is. You may remember it was complicated. It's not. So let's see. One by one. So Okay, balanced three-phase system versus unbalanced three-phase system. What is balanced three-phase system? Three-phase system is nothing but this one. So far we only discussed this one circuit, right? And then we have a phase of a voltage source. Okay, so but here, okay, it looks complicated, but no, we have one circuit, another circuit, and the other circuit. We have three circuits at the same time. They are all same. The load impedance Z are same here, 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 and this voltage source are same, the same magnitude. Okay. The only difference is that this is AC system, so there is a phase angle. So the phase angle of line A, line B, line C are different by 120 degree. That's all. So when the current IA for line A, current B, IB, current IC, they are same. Voltage magnitude VA, VB, VC are same, and this load impedance are same, Z. Then this is called a balanced three-phase system. Okay. Then what is unbalanced three-phase system? Well, IA may be different from IB slightly, or different from IC, or the load impedance, this ZA, ZB, GC are slightly different. Okay. Before talking about the advantages of balanced three-phase system, when can we assume a balanced three-phase system? When? And to use this balanced three-phase system, what should we do? Well, at least you need to make this load side has the same impedance, Z. They should be same, okay? And when you, okay, now this is a very abstract circuit diagram. And suppose that this is one city, another city, the other city, a huge load, okay? And anyway, load changes over time. And for balanced three-phase system, the load here, there, should be same all the time. Okay. When okay, so is it physically possible, mathematically possible, approximately possible, when we have an aggregated load? Okay, so anyway, so let's assume that balanced three-phase circuit system is possible. Especially in the transmission system, that is possible because we have a lot of aggregated load and aggregated generation. But in the distribution network, it may not be possible. So in distribution network, we typically experience unbalanced three-phase system. That's real. Okay, transmission network is balanced, is almost the balanced three-phase system. But in distribution network, it may not be true. What is the advantage of balanced three-phase systems? A balanced three-phase systems has three voltage sources with equal magnitude, but with an angle shift of 120 degree. And equal loads on each phase, no, this is an assumption. Equal impedance on the lines connecting the generators to the load. Okay? And these bulk power systems are almost exclusively three-phase system. Bulk means we have a lot of aggregation, okay? Transmission line, huge power system, almost. Single phase is used primarily only in low voltage. Low voltage means distribution network. And low power settings such as residential and some commercial case. But single phase transmission is still used for electric transmissions in Europe. No? But anyway, balanced three-phase system is more efficient than single phase transmission system. And let's see why. And how much more efficient balanced three-phase system over single phase system. How much? In terms of efficiency, how can we define the efficiency? So, okay. Do we have an answer here? No. So the answer is, okay, the installing the transmission line incurs cost, especially the copper, the material cost. And if you use balanced three-phase system, using the same amount of copper, you can transmit double power. Okay, so the efficiency of balanced three-phase system over single-phase transmission system is 2. You can deliver double power using the same amount of copper. And let's see why. Okay. Yeah, but by the way, here you see an interesting line here. We have line A, line B, and line C, and we have 3 voltage sources and 3 loads components. What is it? That is a neutral line. That is called neutral line. And in an ideal balanced three-phase system, we don't need to have this neutral line. The reason is because the current is 0, surprisingly. Okay? And let's see why that happens. Okay, IA, IB, IC, and this is IN. So incoming current is same to all outgoing current. So outgoing current are IA, IB plus IC, right? And they should be equal to IN. Suppose that we have that line, neutral line, and also IN. Okay, we have this one. Then what is line current? IA. That is the voltage. VA. By the way, here the notation is VAN is. This is node N, and yeah, the voltage difference VAN. Voltage at this point with respect to this node, that is the notation of VAN. So, and then this is VBN, the voltage here with respect to that point. So we know the voltage here and there, and then we know this impedance. Then we can compute the IA like this, and IB. The only difference is that the voltage angle is minus 120 degree. And here, this is 120 degree. Okay, so this one and that one. You see what? The sum of these 3 is 0, right? So the neutral current is actually 0. The neutral current 0 means that we don't need to have this line at all in ideal case. So then can you see why the transmission efficiency is doubled in the case of balanced three-phase system? Same voltage, same current, and same load. Then in this case, ideally, you only need to have 3 wires. No neutral line is required, right? Using 3 wires, you can deliver this amount of power, right? But if you need to provide same amount of power using 3 single-phase system, then you need to have 1 voltage source, 1 node, another voltage source, another load, another voltage source, and another load. This is a VA and VB and VC and Z. It requires 6 wires, right? So it requires double copper lines. Okay. 1, 2, 3, 4, 5, 6. But this one and this one and this one are merged together in three-phase system, and actually there is no current on the neutral line. Okay, so it is something like magic. And then from practical side, still we need to have this neutral line. Why is that? Why? 민재? Yeah, in reality, there is a slight unbalancing, right? So there is some small neutral current, but that IN neutral current is much, much, much smaller than IA or IB or IC. That means the diameter of line A, line B, line C is like that. Then the neutral line is just this much. It uses much less copper. So when you drive through highway, you can see the transmission tower looks like that, and then the number of arms are the multiples of 3, right? Phase A, phase B, phase C, phase A, phase B, phase C, something like this. But you will see a neutral line here. It's a tiny narrow line. Okay. Here, Vxy means the voltage at the point X with respect to point Y. Any questions? No questions? Advantages of three-phase system: can transmit more power for the same amount of wire, twice as much as single phase. Total torque produced by three-phase machine is constant, so less vibration. Actually, you don't know what that means, right? So, because you are using only single phase system, here the 220 volt, that is for single phase system. But you also know 380 volt. This is another popular voltage in the distribution network. There are three-phase motors, so let's see what that is. 삼상 모터. So this is a typical three-phase motor, which is used in a factory. In a factory, they typically use 380 volt, because this kind of motor requires 3 wires, not 2 wires, 3 wires, because this is a three-phase machine. Okay, and this kind of three-phase machine is more efficient. It has less vibration. I don't want to go into the detail, but the total torque produced by the three-phase machine is constant, so less vibration. Okay? And three-phase machines use less material for same power rating, and three-phase machines start more easily than single-phase machines. Okay? So in a factory or where a lot of power consumption is required, this kind of three-phase machine, especially the motor, are typical. Okay. Now, in three-phase case, you may remember you learned this before, delta connection and Y connection, right? And then you remember you memorized some formula for that. So we have a voltage source here, and then load here, and the power system is three-phase system. That means voltage source side, you have this is a source. This is a load. And three-phase system. So phase A, A, B, C, A, B, C, A, B, C. Okay, so B and C. Generator and load. And inside here, you can either use Y connection or delta connection. You remember that, right? Y connection and delta connection. Y versus delta. delta. 한국말로 하세요. You see Y connection and delta connection, right? So in the case of Y connection, here we have a neutral point, one generator, another generator, the other generator like this. So VA, N, here the VBN, here VCN, right? And the load side, you can have either this kind of Y connection, or you can have delta connection. Delta. Typically, this is the load side, and so okay. Typically, at the load side, physically this is delta connection. Typically, at the source side, we have a Y connection. Okay, but when we have Y connection here and delta connection there, you think it's not easy to analyze. Why? Or analyze it. How? The impedance Z. Okay, voltage magnitude V, 120-degree difference. Can you compute this current IA, IB, IC? Actually, in this balanced three-phase system, the magnitude of IA, IB, IC are all same. But in this case, how can you compute IA? 이게 불편하게 그러고 있어요. 아니 그 손으로 계속 뭐 이렇게 잡고 있어요. 그 뭔가 you should not do that all the time. 우리 카메라 감독님이 계속 이러고 있었단 말이야. 거의 모세 수준인데. Anyway, so how can you compute IA, IB, IC? What you need to do here? Yeah, so you need to change these two Y connection, and then you have loop A, loop B, and loop C. Okay. Now you remember how this Z delta is is related with ZA or ZB or GC. 3 times or 1/3, something like that. But anyway, you need to, I will give you a homework problem to derive that. Okay? So anyway, three-phase Y connection, especially at the source side, there are 2 ways to connect three-phase system. I told you voltage VAN, VN, CN. Our reference angle alpha, and then A, B, C, A. So clockwise, minus 120 degree and plus 120 degree. So yeah, here we assume alpha is 0 here. So VAN and VBN minus 120 degree, and this is VCN 120 degree. And this is called line voltage, VAB. So the voltage at line A with respect to line B, VAB. Okay? And then this is a VAN minus VBN. So VAN, VBN, this minus that is this arrow, and that is same to this arrow. And you see that the length of that is, okay, so phasor notation, another phasor notation, and the result is when you calculate the vector sum, you have this result, this VAV. So this arrow or that arrow, the magnitude is square root 3 times, and then this angle is alpha plus 30 degree. And visually you can see that this angle is 30 degree, right? So this line voltage is related to this phase voltage in this way by square root 3. Similarly, VBC, VCA is that. VBC, where is it? Here, yeah. VCA here. So yeah, AB, BC, CA, so minus 120 and plus 120 degree. Y connection continued. So yeah, this is called a phase voltage, and this is called a line voltage. And line voltage is square root 3 times phase voltage. Okay. Yeah, line voltage is square root 3 times phase voltage, and then yeah, for this case, the 30 degree difference. And in the case of voltage, we have this relationship, but in the case of current, the I phase, I current are same. Actually, we don't need to introduce this notation. Okay, phase voltage and phase current. In the three-phase system, the delivered power is 3 times of power delivered on each phase. And because this is balanced three-phase, for phase A, B, C, all the delivered powers are the same. So each one of them, V phase times I phase conjugate, and 3 times of that is the total delivered power. Delta connection. This is the load side here. Okay. So yeah, Z, Z, Z. Why does the load looks like that? Because you are using three-phase machine. Three-phase machine inside is like that. You have a motor here, magnetic component, another magnetic component, another magnetic component, right? By the way, have you ever seen three-phase motor before? I just show you the photo, right? So you already forgot that? Yeah, this is three-phase motor, okay? So inside of this three-phase motor is like this, okay? The inside of that motor is not like a Y connection. The inside of the motor is delta connection. So, yeah, IA, IB, IC, like that, and we define the line, line current IAB is this one. IAB. Then IBC, ICA, right? Yeah. And then IA plus ICA equals IAB. Kirchhoff current law, or IA equals IAB minus ICA, right? So we have this one, and IA. IB, IC, and IA, AB, BCCA. This is your homework by Thursday. Okay, derive this. In same things. And at the load side, the delivered power is 3 times V phase times I phase conjugate. Okay. So here are 3 phase examples. Assume that delta connected load, the 3-phase inductive motor, with each leg Z is 120 ohm, is supplied from 3-phase 13.8 kilovolt. That is a line-to-line voltage. Okay, so what is it? This is your 3-phase inductive motor here. This is the pole in the street. Okay, so when you look at the pole, you have 3 transformers for 3-phase. Okay, but so this is a pole, and then actually you typically see this kind of transformer. Okay, and in some case, for example, this is a factory. Yeah, this is a factory. And then, it consumes huge power, and then they have all these 3 lines from each transformer because it wants to use 3-phase machines. Okay, but this is a house. This is another house. By the way, this is a 22.9 kilovolt distribution line. Okay, so this is a 20.2 kilovolt distribution network, and then for this factory case. Actually, what I wanted to draw was something like a factory. You know what I mean. Anyway, so this is 380 volt, 3-phase. But here, this is 220 volt. So we have another distribution line, another distribution line, and another distribution line. So this is called feeder. Okay, so many houses are connected like that. Another load here, here, here. Okay. So please pay attention to. This is a single-phase system now. Still, this is 3-phase system. Okay. Yeah. So, yeah, the line voltage VAB or VBC, VCA are 13.8 kilovolt. And this load is 100 and the phase is that much. This is the inductive load motor. So the line current IAB is a voltage over impedance. Okay. This is actually, this value is already computed for you to compute this easily. Okay, so just provide it, and the impedance is that. So line current is that, Another line current is that. You see the same magnitude and the 120-degree difference of phase. And continued. But this is a line current, but we want to compute the phase current IA, this one, or IB, IC. And actually that is, this is a, yeah, no. Using that one, yeah, you can compute IA, IB. Just math, simple. And then the total delivered power is 3 times the, either 3 times, yeah, same thing. So 3 times of line voltage times line current conjugate. Okay. So VAB is provided. IAB was computed here. So conjugate this much. So this is the total load consumption at the load side. And in this case, what is it? This is the complex power consumed at the load side, active power and reactive power. So you can compute the power factor here. And power factor is 0.94. This is pretty good. Sometimes power factor is really bad. No, I was surprised that I was surprised to note that some factories have power factor like a 0.5. 0.5, power factor 0.5. That means, what does that mean? Then this is a 60 degree. So in this case, the power factor is 0.5, right? And it happens in real situation. The angle is 60 degrees, so very, very inefficient case. So in that case, we can put reactive power at the load side using STATCOM or SVC. Okay. Delta Y transformation. So, okay, we have a Y connection at the source side and the delta connection at the load side, but to make the analysis easy, you need to convert delta to Y or Y to delta, depending on the situations. So to simplify analysis of balanced three-phase system, delta connected load can be replaced by Y connected load, and this is the formula. So yeah, Z Y is 1/3. This is the result, but you should derive that. Check the textbook, okay? By Thursday, this is Tuesday, by Thursday, I don't want to derive that for you. And for delta connected source, the delta connected source can be replaced by Y connected source. Actually, yeah, like this. Derive that as well. Actually, here is the proof. So why do you need to do that? Yeah, so why do you need to do that? Let me stop here. And you do the homework. And which one do you want? My question was, do you want to do the homework on your own? Sure. Then we can say 5 minutes. Because I will stop now. Yeah, so let's see. Delta Y transformation proof. No. Yeah, this is delta connection, this is Y connection. And then, okay, you see what's going on. Suppose the two sides have identical terminal behavior, and for the delta side we get IA, again, now using this one, IA is IAB minus ICA, and IAB is VAB over Z delta. Right? So that's this, and the VAB minus VCA is that. And hence Z delta is VAB minus that one, okay? And for the Y side, this is delta side. For Y side, we get VAB is ZY. VAB, this one, ZY times. VAB, this one. Okay, so change this to that, but still, no, the voltage here is VAB, and then this is changed to that. So, and current IA, IB, IC. Please focus on the direction IA, IB, IC. So VAB is ZY, no, VAN minus VBN. So this one is a VAN, this is VBN, right? So you have this. Similarly, VCA, you have that. So this minus that is that. So I don't want to go into the details. You can just read this. So this is the result. So you don't have a homework. Good for you. Thank you. I'll be with you on Thursday. Okay. Any questions? No questions. Okay.